Bien, bonjour à toutes et à tous. Je m'appelle Jacques Lanares, je suis vice-recteur de l'Université de Lausanne et notamment en charge de la valorisation de l'enseignement. Donc vous imaginez que je suis particulièrement réjoui de vous voir aussi nombreuses et nombreux pour cette conférence, puisque c'est quand même un gage d'intérêt manifeste. Je voudrais vous souhaiter la bienvenue dans cette session au nom des 3 organisations qui ont mis sur pied cette conférence, la HESSO, le SFDN, qui est le Swiss Faculty Development Network, qui regroupe l'ensemble des conseillers et conseillères pédagogiques des hautes écoles suisses, et bien sûr l'Université de Lausanne. Je voudrais excuser l'absence de la conseillère d'État Anne-Catherine Lyon, qui était très intéressée et qui finalement ne pourra pas venir. Bien, sentez-vous chez vous, vous êtes chez vous, profitez de cette matinée. J'aimerais remercier les personnes qui se sont beaucoup impliquées dans l'organisation de cette conférence, le comité d'organisation qui était là, Nathalie Cheny, Emmanuel Sylvestre, Ingrid Leduc et Ariane Dumont qui est là et qui a initié ce processus. Donc je suis très reconnaissant de ces efforts pour que ça puisse avoir lieu. Les 3 organisations que j'ai mentionnées, la HESSO, le SFDN, l'Université de Lausanne, sont toutes 3 très intéressées par améliorer l'apprentissage, l'enseignement supérieur et donc aux démarches d'innovation. À une époque où moins de 3% des étudiants et des étudiantes vont faire une carrière académique, on ne peut pas juste se contenter de former la relève par contamination de grands chercheurs. Il faut aussi s'occuper des autres et ça veut dire donc s'assurer qu'un maximum d'étudiants et d'étudiantes arriveront au bout de leur cursus avec les meilleures compétences possibles. Et ça sous-entend d'investir dans l'enseignement, dans l'apprentissage, ça veut dire innover dans l'enseignement. Vous savez probablement qu'au cours de la deuxième moitié du siècle dernier, les recherches en psychologie, en éducation, ont constamment souligné, mis en avance l'importance de l'implication, de l'activation des étudiants et des étudiantes dans le processus d'apprentissage. Il y a des tonnes de littérature là-dessus. Mais c'est un processus qui ne se fait pas si facilement, et qui demande de changer et les mentalités et de trouver aussi des moyens de le faire. Et cette évolution des conceptions se retrouve aussi renforcée en quelque sorte par le processus de Bologne, parce que Bologne, on la voit un peu 3, 5, 8 et des choses un peu administratives, mais en réalité, l'orientation sur les learning outcomes, l'orientation sur le CTS, c'est-à-dire qui prend en compte l'activité des étudiants, renforce cette vision de l'apprentissage qui met l'étudiant et l'étudiante au centre du processus, Student-Centered Learning and Teaching. Dans ce contexte-là, évidemment, l'apprentissage coopératif, peer instruction, est particulièrement pertinent. Et de ce fait, nous sommes évidemment très très heureux de pouvoir accueillir aujourd'hui professeur Eric Mazur, qui est professeur de physique à Harvard. Je me permets de parler français parce qu'il parle le français aussi bien que moi à peu près, donc et qui est un pionnier de l'enseignement coopératif. Et donc il a une grande expérience et c'est vraiment très stimulant de pouvoir l'écouter parler de cette expérience. Et il y a un autre aspect que j'aimerais souligner, c'est qu'il s'inscrit tout à fait dans ce qu'on appelle maintenant Subtle Scholarship of Teaching and Learning, qu'on n'a pas toujours pas traduit en français, qui dit simplement qu'on doit étudier le processus d'apprentissage scholarly, et que donc on doit faire de la recherche sur son enseignement et faire évoluer son enseignement en conséquence. Et c'est un exemple tout à fait magnifique de cette démarche qui, bien sûr, on souhaite partager par de plus en plus de collègues pour faire évoluer l'enseignement supérieur. Donc, il est vraiment pionnier de toutes sortes de façons. Vous le savez, je l'ai dit, il est professeur à Harvard. Je pense que c'est la chaire Balkanski. C'est juste. C'est bien, j'ai beaucoup de mal avec ces choses. Merci Eric. Et je vais lui laisser la parole, bien sûr, parce que vous n'êtes pas venu pour m'écouter, pour nous présenter les choses. Je dis juste 2, 3 petites... Si vous partez en courant après la conférence, avant l'apéritif, ou pour vous jeter sur l'apéritif, il y aura un article dans Le Temps du 27 octobre, une interview d'Éric Mazur, que vous relire. Si tout va bien, il y aura en ligne cette conférence. Si tout va très très bien, peut-être même ce soir. Il ne faut pas rêver bon marché, il faut rêver cher. Hein. Voilà, et on envisage de constituer des groupes de collègues intéressés à ces questions d'enseignement d'apprentissage coopératif. Donc vous pourrez être invité à participer à ça. Juste un dernier petit point, quand vous souhaitez poser des questions, prendre la parole, ayez la gentillesse d'attendre un micro et des personnes qui amèneront les micros, parce que sinon c'est un peu difficile de tout comprendre. Bien, merci d'être venu. Et surtout, merci Eric de prendre du temps dans un emploi du temps très, très, très chargé. Eric est évidemment très, très sollicité. Donc, thanks a lot. The floor is yours.
Thank you.
Non, tu n'as pas besoin.
Wow, there are a lot of you here. I guess you must all like public confessions. You know, it's kind of intimidating to be confessing in front of so many people. I'd rather be doing this one-on-one. I guess I just have to remind myself of the American proverb, the more you confess, the more books you will sell. So, let me start with these confessions. Actually, the first one is not pertinent to the subject of my talk. The first is that le français, c'est ma langue maternelle. But it would be really difficult for me to give this talk as effectively in French as I do it in English, because I've lived in the US for, what, now 32 years. And my French vocabulary is narrowed, and there are so many terms, misconceptions, education, this and that and the other, that I don't know in French. So my apologies, but if you want to ask a question, feel free to do it in French. So my first confession. When I started teaching at Harvard 29 years ago, I never asked myself the question, how am I going to teach? That's kind of strange, right? Because when you start doing something new, the first question you should ask yourself is, how am I going to do it? That question did not come up in my mind. To me, it was perfectly clear what I was going to do in the classroom. I was going to do to my students what my professors had done to me. Lecture in a space not very different from this one. And I think it's a very natural thing to do. We tend to project our own experiences onto the world around us. And I naively, for it was very naive, naively thought, I learned it in a classroom not very different from this one, so that's how people learn. And what happened was that very quickly I got feedback that I was doing the right thing. You know, I was asked to teach a course that none of my colleagues wanted to teach. I didn't know that when it was physics for pre-medical students. These were not students who wanted to learn physics. They had to learn physics. They hated physics already before coming into the classroom. Now, what are the ways in which we evaluate teaching? I can think of two of them, the traditional ways. One is the end of semester questionnaire. I'm sure you do the same thing. You give a form to the students, you know, and you ask how much they like the course, how clear the lectures were that were given by the professor, and so on. Most of my colleagues came close to committing suicide when they taught this course at the end of the semester. But not so for me. I got 4.5, 4.8 on a 5-point scale. Clearly, the students liked what I was doing. So that's one metric. The other metric was my students' performance on examinations. Now, usually, when physics is taught to pre-medical students, you know, the level of the course is lowered a little bit. Not so at Harvard. We use a full-blown calculus-based course. I could give these students some really hard problems using triple integrations, complicated objects. I mean, I won't bother you with the detail, but let's say that some of the problems I wasn't sure I would do well under the time pressure of an exam. But by and large, the students did well. So they liked me as an instructor. did it well on what I considered complicated exam questions, obviously I was doing the right thing. And that illusion, because let me tell you, it was an illusion, continued for many, many years. Now, in retrospect, there were always some negative signs. But I'm a positive thinker, so if I get positive signs and negative signs, I ignore the negative ones and focus on the positive ones. Let me give you some examples. Each year, even though they would give me a high rating, some students would write in the bottom, there's a comment section where you can write whatever you want. They would write, "Physics is boring," or "Physics sucks." I mean, how can you think of physics as being boring? What is more interesting than understanding how the world around us works? I couldn't make any sense of those remarks, so I just ignored those comments. Same thing happens when I go to a party and people ask me what I do for a living, and I tell them I'm a physicist. Physics? I got such a hard time with physics in high school or in college. Or my dentist, and you know, I couldn't even talk back because I had the thing in my mouth, right? He said, "Oh, you're a physicist. I got an A," which I guess here would be a 10, right, "for physics in college, but I really didn't understand anything." It always creates a feeling of embarrassment, and I was never able to understand it. And because I wasn't able to understand it, I ignored it and continued that way on and on and on. Now, I've used the word physics already way too many times. This is not a talk about physics. It's a talk about education and about how I changed my approach from being a lecturer to being somebody who is basically a coach helping students learn. Now, you all have one of these little clickers in your hand, and there's always a danger starting a talk on education with technology, because the investments that are now being made in technology for education are, in my view, totally ridiculous, especially because most technology in education is simply old wine into new bottles. Doesn't taste any better. And it doesn't, you know, give any better education. Classrooms, fortunately not this one, but many classrooms get equipped with smart boards. Well, would the information coming off a smart board go more easily into the brain of the students than a blackboard or a whiteboard or an overhead projector or PowerPoint? We don't need smart boards, we need smart students, right? And lots of uses of technology are simply a new way of doing old things. So the talk today is not about technology. You have that technology because we're going to have some fun with that technology, but it's really about the pedagogy. And there are many ways of using this technology completely incorrectly. I'm going to use it initially simply as a survey tool because I want to start this, this colloquium by having us all reflect on our own education. So I'm going to ask you to do a little exercise. I would like you to take a little piece of paper or something to write on. And on that little piece of paper, I want you to, oh, before we do that, actually, let me explain how those clickers, les zapettes, I keep forgetting how you call it in French, work. There's no on-off button. They're always on. And I'm going to ask you a multiple choice question, and you're going to press one of these buttons. Stay away from the channel button. The channel allows you to change the channel in case, you know, neighboring classes all use the same clickers. You don't want students in this class to be voting in the class next door. It is possible, but you don't want that. So we want to be on channel 41, which should be displayed in the window. If you press accidentally the channel button, this little light will flash rapidly. Just wait until it stops flashing, and then you'll be okay. If you press a button, anyone, it will show in the window the button you have pressed. So if you press 5 or E, you'll see 5 or E in the window. That's all. Even students can do that, believe it or not. Let me show you what I see as a professor on my screen. I have that little window that floats in top of it. I've opened the polling, which is why this is now a stop button rather than a start button. And as people press a button, why don't you press a random button? Go ahead, press a random button. You can see this number go up, right? So we have now 156 people who have pressed the button. If you press a button and then press another one, the counter will not increase because the only thing that happens is that the second click replaces the first one. Right? So if you answer a question and you press, let's say, 2, and you think, oh no, it should be 1, and you press 1, the 2 gets erased and the 1 replaces it. At any time, I can press on this little button here and see a distribution. I see many of you like button number 5. Why don't you all press 1? Go ahead, press 1. Very good. You're good at following instructions. I like that. Notice how the distribution instantly reflects that change. 5 is disappearing here. There's still some people who are resisting here. And before more of you start resisting, I'm going to press the stop button here so as to freeze this distribution. Now, if you click a button, you won't see 5E, but you see a circle with a line saying the polling is closed. That's it. So that's all there is to the software, which is great because you don't want to be dealing with complicated things when you're standing in front of the class. Now, there's one other thing that happens. When I press this stop button, the software stores the distribution, it stores the individual responses, but it also stores a picture of whatever is in the background. So I know that tonight, if I review the data, that these data belong to this screen. This means you can use it with any presentation software. You don't have to use PowerPoint. It could be a Word document. It could be, in my case, it's a PDF file because I don't like PowerPoint. I just use a PDF file. It can be anything, anything you want. Okay. So one more thing. Turn the clicker around and look on the back side. You'll see that there's a barcode. That barcode is unique. There's only one barcode like the one you have in front of you. So you may think that you're anonymous here. I'm sorry. Well, no, we don't know who you are because we just randomly distributed the clickers. But in a real class, you could ask students to enter this barcode together with another identifier, their email or their student ID number, and you are actually able to track individual student responses. Okay, so now the little exercise. Take a little piece of paper, and on that little piece of paper, I want you to write something you are really, really good at. It could be anything. It could be interpreting medieval works of art. It could be solving partial differential equations. It could be string theory. It could be cooking, or it could be public speaking. Anything. You know when you're good at something, right? Because A, you derive pleasure from doing it. And secondly, you know that other people respect you for it. Ah, there's Eric. He's good at blah, blah, blah. Right? I mean, you sort of feel that. Ideally, I want you to write down something that has been important in your career. So unless we have bakers or cooks here, the cooking will probably not be in there. But write that down and then fold it up. It's private information. You will not have to reveal it. You don't want your neighbor to see it. But do commit to it. And you're all successful individuals, so it shouldn't be too hard. One thing. If you're very successful and there are hundreds of things you can write down, just pick one. Oh, if you want to make a drawing instead of text, that's fine too. I just want you to commit to one skill that has been important to you and that you're good at. Okay, so does anybody need more time? Okay, so now that you've committed that, just fold it up. You don't need to reveal it. It's private information, so you can be brutally honest here. We can do the next question. The next question is hard. Because now I want you to think about how you became good at whatever it is that you wrote down. What were the circumstances that led you to develop that skill or knowledge or whatever it is that you wrote down? How did you become good at it? I want you to write a few words about how you learned that, how you developed this. Way, many people are just sitting there. Because, the things that we enjoy, we learn without really being aware of how we learn. We own the learning, rather than somebody telling us, You learn that because it's good for you. So I want you to write down in a few words how you became good at it. I have done this little exercise all around the globe, and it's really interesting. You know, I've done it in South America, I've done it all over Asia, a few months ago I was in South Africa, I've done it all over Europe, I've done it all over North America, I've done it in Australia. And let me tell you, there are no cultural differences, because I have collected the answers to the second question. There are no cultural differences, which is actually not surprising because we're all wired to learn as human beings, and our brains are not different. Yes, there are cultural differences, but there are no cultural differences in learning. So let's actually see if this part of Switzerland is different from the rest of the world. I doubt it, but you never know. And I'm a scientist, so I like collecting data. So I've collected the answers, and they typically fall into the following 4 categories. I became good at it by trial and error, by trying it, you know, and then making errors, learning from my errors. I learned it by listening to lectures. There's no listening on the screen there, but it's important, right? Because there's a big difference between giving lectures and listening to lectures. I became good at it by practicing. I became good at it by apprenticeship, by working along with somebody who's really good and then learning from that person who is the master. And then there are lots of other categories like family and friends and this and that and the other. I would like you to make a choice between those 5 options and choose the one that comes closest to what it is that you wrote down. So please make a selection, and I'll give you another 10 seconds. 5. About 180 here. I know we have a little bit more people, but that's okay. Here we go. And sure enough, it's no different from anywhere else in the world. We learn by practicing. Typically, that 3rd bar is between 55 and 72%. So you're no different from the rest of the world. We learn by practicing. We learn by doing. But that's not why I did this little exercise. Because there's something else really, really interesting about that distribution there. What is it? Look. What is it? There's something else that stands out. What is it? Lectures, exactly. Only a poor 2 people, and I pity them, chose lectures as the way of learning. We'll get back to the lecture in just a second, because right off the bat here, we see that there's something really interesting, because how do we teach? This is how we teach. This is a picture of me teaching my pre-med course, long time ago. BC, before computers. See, I'm using an overhead projector rather than computers. So we see something really strange here, right? You have chosen a skill that's important in your career and said that you learned it by practicing, not by lecturing. Yet, all around the globe, and again, there are no cultural differences there, we mostly teach in a setting that dates back to the Middle Ages. I mean, in fact, it dates back to the ancient Greek, right? Amphitheater. We are in the Amphipôle. What is this building called, right? The amphi is in there, right? So it dates back to the ancient Greek, who were smart enough not to use that space for teaching. They used it for performances. If you've ever seen a painting or a representation of the School of Athens, you don't see an amphitheater. You see people walk around in pairs teaching each other. So we see that there's something really interesting going on there. So here's what I would like to do. I would like to talk a little bit about education. What is education? What do we mean exactly when we use the word education. Imagine that I ask you now, on that little piece of paper, to write down a short definition of the word education. I think many of us would struggle. We know exactly what is meant, but to articulate that is really hard. You look up definitions of education, they're all over the place. I like one given by psychologist Skinner, an ex-colleague of mine at Harvard, who said, education is all that is left after all that is learned is forgotten. There's a deep truth there. After talking about education, I'll talk about peer instruction, what I did in my classroom in response to the rather disheartening discovery that my students weren't learning. And then, as in any academic enterprise, there'll be a test at the end. So you better pay attention or you'll be in trouble. So let's start by talking about education and ask ourselves this question, given that education is, lecture is being used as the primary vehicle for instruction, I think a good question to ask is, what is it that actually happens in a lecture? Let's go back to that picture of me teaching. I would like you to give me a description of the process that is taking place on the screen behind me. And ideally, I want you to use a verb. But there are two verbs I do not want to hear, teaching and learning. So you'll have to use another one. So go ahead, just blurt it out. Talking. Oh, too many at the same time. Listening, talking, listening. Motivating, demonstrating. Watching, instructing. That's the same as teaching. Did I hear somebody say sleeping? My students are not sleeping. But I will actually come back to the word sleeping twice at the end of my talk again. But there's something, a really interesting quote that was given a while ago. Certains hommes parlent pendant leur sommeil. Il n'y a guère que les conférenciers pour parler pendant le sommeil des autres. Now, if you look this up on the web, it often says Albert Camus, but it turns out it's not Albert Camus. It's Alfred Capu, who was a Parisian journalist. But no. My students are not sleeping. So I want to hear some more terms here. Sharing. Performance, which is what this space is designed for, right? Interacting. Is there really much interaction? I'm working hard here, and we are interacting somewhat. But, I urge you to step into a random class in this building or in a similar building elsewhere, sneak in the back, and observe and ask yourself how much real interaction is going on. Very, very, very little. Occasionally you have the lecturer who stops and says, does anybody have a question? And students look down because they don't want to make eye contact, right? So I think very little interacting. Daydreamer, we'll get back to sleeping. Waking up to curiosity, maybe somewhat, yeah. A lecture and a performance can certainly be motivating. Transferring. Transferring what? Transferring knowledge. But what is knowledge exactly? How do you transfer knowledge, right? I think transfer, we're getting very close to where I want to be. But I don't think you can transfer knowledge. Information. Lectures focus on the transfer of information. And you know what? My students had told me that in the second year that I was teaching, and I had ignored it. You see, when I started teaching, I didn't ask myself how. What was the question, do you think, that did come up in my mind? Right? I mean, somebody tells you you're going to teach introductory mechanics. What exactly, or more precisely, what book? So I went to a colleague who had taught the course before, and I asked him, what book did you use? And he said, oh, in this course we've used Halliday and Resnick. The physicists among you probably know that book. Now, I was educated here in Europe, in the Netherlands, And I don't know how it is in Switzerland now, but in the Netherlands, you would never buy, as a student, a textbook for an introductory course. Why buy the book if the professor is presenting the book to you? But I was told that in the United States, all the students bought books, and that I should make sure that the bookstore had enough copies of the books. So for those of you who know Harvard Square, there's a bookstore called the Coop. I went to the Coop, which also orders a textbook for the students, and I said, be sure that you have 150 copies of Haldane and Resnick at the beginning of the semester. And as I walked back to my office, I thought, wait a minute. If the students have the book and I have the same book, then what do I do in the class? So I knocked on the door of my colleague and I asked him that question. And he said, oh, don't worry. There are lots of different physics textbooks. And he showed me a shelf full of books. So I started looking and I quickly discovered the perfect textbook. It was perfect for two reasons. One, it had a different approach. So it wasn't just regurgitating the same book to them. But more importantly, the book was out of print. They couldn't get a copy of it. So for each class, I spent 10 hours preparing lecture notes. And in class, I would either project the notes on the overhead projector, or I would write them on the board behind me. Now, because my notes were different from the textbook, I said to myself, I better give a copy of the lecture notes to my students so they have a record. So at the end of each class, as they walked out in the back, they could grab a copy of my lecture notes. Now, why do you think I handed them out at the end of class rather than the beginning? To listen to me. I didn't want them to take the notes and go back to bed. But if you stop to think about it, isn't that already admitting that there's a problem? Why force them to get the information out of my mouth if they could get the information from the notes? Anyway, that was not coming up in my mind. But what did happen was that after a few weeks, some students came to me and said, Professor Mazur, could we get a copy of your lecture notes at the beginning of each class? This way we don't have to write down that much. And I had indeed noticed that each time I wrote A on the board, 150 pens went A in the notebooks of the students. I once heard somebody describe the lecture as a process whereby the lecture notes of the instructor get transferred to the notebooks of the students without passing through the brains of either. Anyway, that year went by. I got my high evaluations. And you know what happens when you have a high evaluation. You get punished and asked to teach that same course again. So the next year, I was asked to teach that same course again. And I was preparing for the semester. I said to myself, you know, this year, I'm not going to hand out the notes lecture by lecture. A week before the semester starts, I'm going to send the entire collected set out for duplication. And on day one, the students get the entire packet of notes for the entire semester. You know what the unexpected result was? The unexpected result was that about half a dozen students wrote on their evaluation questionnaire, Professor Mazur is lecturing straight from his lecture notes. Hello? I mean, what was I supposed to do? Develop another set of lecture notes that was different from the lecture notes I gave to them? I was so mad. But you know, they had a point. They were right. I was focusing on the transfer of information. Now, given that I would say 99.9% of all classes taught around the world focus on information transfer, we could ask ourselves the question, is that what education is? Is education just the transfer of information? You know, I hadn't thought of doing that, but why don't we try it? Let's see. If you think that education is just the transfer of information, you press 1. If you think education is more than just the transfer of information, you press 2. Let's see where we stand here. So 1, education is merely the transfer of information. 2, There's more to education than just the transfer of information. 3? And there we have that 3% again. Now, to those 3% who chose yes, I have to warn you, you will be out of a job very soon. Because let's for a moment hypothesize that education is just the transfer of information. If that is true, we will all lose our jobs very soon. Because what would be the logical thing to do if that were true? What would be the logical thing to do? Distance learning, or we just videotape the best possible lectures, right? I mean, one in French, one in English, one for different fields. From time to time, you have to redo them because clothing gets out of fashion and so on. But, you know, why reenact the same lecture over and over and over again? Just videotape it, put it online. What would you lose by doing that? What would you lose? Interaction. But you know how much, we've already discussed that in a sense, right? How much interaction is there really? Go, I really urge you to do this. Go and do some, what I call academic tourism. Step into random classes of colleagues you do not know. Just sneak in the back, you know, and observe. You will be surprised. I do it regularly. It's very illuminating. You learn some good ideas, presentation ideas, but you can also see from the back, you get a very different perspective that things are really, really wrong. So I think, yes, you may lose a little bit of interaction. A little bit, because it's always the same person in the front row who raises his hand, right? The rest of them is not involved. What would you gain? You would gain a lot. Because now students can take in the information whenever they are ready. Not whenever the classroom is there, right? Whenever they are ready. And they can do it. You don't have to have hour blocks. You can do it in 7 minutes, 10 minutes, little conceptual blocks, logical units. It doesn't have to be time units. It could be logical units rather than time units. But there's another huge benefit. You can actually think. Have you ever had a student in your class raise his hand and say, "Professor, could you please be quiet for 5 minutes? I need to think." I don't know about you, it's never happened in my classroom. But online, you can hit the pause button and think. Does this make sense? You can't do that in the classroom because you have this continuous stream of information coming at you. Or have you had a student raise his or her hand and say, "Professor, could you please repeat the last 10 minutes? I need to hear it again." It doesn't happen, but online you can easily do that. Scroll back, listen to it again. Or you can hit the pause button, call your friend and say, "Hey, do you understand what Professor Mazur says at 8 minutes and 21 seconds? I don't understand it." So all of these things you'd gain. So I'm afraid for these, I'm very afraid for this 1% here, but I'm also afraid for these 3% there, you know, because I think if education was just a transfer of information, we have a problem. Fortunately, 96%, me included, think there's more to it. Now, I know I've picked on the 3% and the 1%, but now I have the 96% in the corner, because if education is more than just a transfer of information, what is it? What do you need in addition to it? Experience? Explanation? Loud, I can't hear from here. Patience? Or patient? Okay. Imagination? Understanding. You need to do more than just, you know, open your skull, take the information in, and close your skull. So something needs to happen. As a learner, you need to do something with that information. So much of education is simply instructors delivering information to the students. You wait 2 months, You put students in an exam room, separate, you cut them off from information, you cut them off from each other, and you ask them to regurgitate the same information back. Take history. I mean, I learned history in Holland, and I think in Europe in general, we pride ourselves in providing a good education. I've forgotten everything that I learned in history because it was mostly memorizing years. In 1660-something, I'm sorry, I forgot, the Dutch defeated the British in the River Thames. And then months later on the exam, in what year did the Dutch defeat the British in the River Thames? I must have given the right answer often enough because I ended up in college. Did I learn anything? First of all, I forgot the date. I can Google it, but I forgot. Have I learned something of value that makes me a better citizen? Do I know why the Dutch defeated the British in the River Thames? No, I don't. So a lot of it is just, delivering information and then having the students regurgitate it back. A few months ago, I was at a university south of Boston, in Connecticut. I won't be more specific than that. I gave a talk in the physics department, and after my talk, one of the physics professors came to me and he said, I had something really strange happening in my classroom this year. He had worked really hard to make physics relevant for the students. And the way he had made it relevant was by putting it in the context of baseball. Well, there's a lot of physics in baseball, right? Trajectories of balls, collisions between balls and bats, runners running. I mean, you can teach a lot of physics in that context. So in the classroom, he used examples from baseball. On the homework, students had to do exam problems that dealt with baseball. On the exams, during the term, the midterm exams, he put baseball problems. At the end of the term, he was writing the final exam. And as he wrote the final exam, he realized that he had run out of baseball problems. So I put some football problems on the exam. Professor complained to students, we've never done any football problems. You're laughing at it, but probably you do recognize some of your own students, or maybe even some of your own experiences. But let's face it, unless you can transfer what you've learned in one context to another new context, I don't think you have really learned. The true hallmark of learning is being able to take what you learn in one context into a new context. That's sort of the pinnacle of learning, and certainly in institutions of higher learning, like yours and mine, that's, I think, what we hope. And I'm afraid we don't. You had your hand up. I'm sorry. Absolutely. In fact, I'm glad you say that because I was thinking in my head I should point it out and I forgot. Let's think about the exercise we started with today, right? What was the number one choice? Practice. So in a sense, I'm glad you mentioned that. We need to build in practice right in the classroom. Instead, what do we do, or what did I do? You can talk for yourself. I should talk only for myself. I focused completely on the transfer of information. What's the result? Well, it took many years before I actually discovered what the result was. What happened was that in 1990, so after teaching for 7 years, I read in an article about a conceptual survey called the FCI, which stands for Force Concept Inventory. It's a multiple choice test. I generally don't like multiple choice tests, but this one is actually quite well designed, that tests students' understanding of the concept of force. By the way, this is a physics example because I'm a physicist, but what I'm telling you in general is not about physics only. If you're a chemist, you can probably substitute chemistry, or if you're in the humanities, you can substitute your own field. But I have to use an example from my own field in order to tell you what I experienced. So in physics, the concept of force is a very basic one. In a typical mechanics course, you discuss that concept in week 2. If you do not fully understand the concept of force as articulated by Newton's 3 laws, it is very difficult, if not impossible, to make sense of many other concepts, momentum, energy, and so on, right? So if you don't understand that concept in week 2, there's a big problem. Well, let me give you an example from the force concept inventory. A heavy truck and a light car collide head-on. The force exerted by the heavy truck on the light car is A, larger than the force exerted by the light car on the heavy truck. B, the two are equal to each other. C, the light car exerts a larger force on the heavy truck than the other way around. D, they're not exerting any force on each other. They're just in each other's way. Now, you're laughing about that. I think no physicist in his right mind would ever come up with such a crazy answer. But that's the power of the FCI. The way it was designed by Professor David Hestenes at Arizona State University was not by him trying to invent wrong answers. He gave the question as open-ended questions to his students, collected the responses, and then tabulated the most frequent incorrect responses, and this was one of them. Now, in spite of the fact that most students who take introductory physics have no problem reciting Newton's 3rd law, which you may have heard of, action is reaction, or the force exerted by 1 on 2 is equal to the force exerted by 2 on 1, even though they have no trouble reciting that, when you replace 1 by heavy truck and 2 by light car, they forget all about Newton's laws and they revert to their intuitive notion that a heavier object exerts a larger force on a lighter one. The interesting thing, according to the article I read in the early 1990s, was that Hestenes shows that there's not much difference whether you ask this question at the beginning of the term or at the end. Well, I read that and I thought, no way, this has nothing to do. I mean, after all, most of the students who come to Harvard have already had physics a couple of years. This does not pertain to my situation. But, you know, I'm a scientist, so you learn not to make assertions. You learn to, you know, get data. So I thought I better show that in my class at Harvard, things are different. So one day, I stepped into the classroom and I said to my student, look, I'm going to give you a quiz. I didn't want to call it a test. You know how pre-meds are. You say test and they freak out. So I'm going to give you a quiz. And then I said, you don't have to worry about it. It's not going to affect your final grade in any way. I'm just giving it to you to assess the quality of my teaching. And as I said that, I realized I just removed any incentive for them to even participate. I mean, you know how pre-meds are. You tell them it's not going to affect your final grade. They won't even show up. Right? So I thought I better give them a reason to take this test seriously. So I said, look, if you take if you take this quiz seriously, it's going to help you because in 2 weeks, we have a midterm examination, and this will help you diagnose your own understanding and give you a chance to improve your learning. As soon as I said that, I realized I told them a huge lie. I mean, the class was dealing with rotations, and they had to calculate rotational inertia of complicated three-dimensional objects. I mean, we were way beyond the concept of force. And I was afraid that the students, when they would start this quiz, would be offended by the simplicity of the questions. Oh boy, were my worries quickly dispelled, because hardly had they started on this quiz, or one student raised her hand. And she said, Professor Mazur, how should I answer these questions? According to what you taught me, or according to the way I usually think about these things? I had no idea how to answer that question. And by the time the test had been completed, I had been dragged out of my ivory tower. Here are the results. So 1990, I taught a completely traditional course. This is a post-test because we had already discussed Newton's 3 laws. Ideally, you do a pre-test and a post-test, right? Number of students, and here's the score. When I took there are 29 questions, so the biggest score is 29. When I took the test, I got 28 out of 29. I guess I must have misread a question or something like that. I actually made a real mistake. Notice that there are several Harvard students who have full score. Hestenes says that anybody who scores below 23, right here, has not understood Newton's laws, is still partially an Aristotelian thinker, connecting force and velocity rather than force and acceleration. And as you can see, 60% of my class is still an Aristotelian thinker towards the end of the semester. If you were to take a gorilla and put a gorilla behind the keyboard randomly pressing buttons, you'd get about 10. So as you see, we have at Harvard a couple of gorillas in the classroom. Now, we've given this test now for 20 years, and the pre-test is very stable. Here, for example, is an average for about 4 years. You see that there are a few more gorillas early in the term. But notice that if I put the post-test on top of the average pre-test, there is very little difference. I'm going to show you how the data obtained at Harvard compare to those obtained elsewhere. So what I'm going to do is I'm going to take the initial, the pretest distribution, take the average, which is about 70, and put that on the horizontal scale. Then I'm going to take the red distribution, the post-test, and take the difference, which represents the gain, and put that on the vertical. So the pretest is 70%, the post-test is 78%, which means an amazing 8% gain. That's what my students learned about this very simple subject discussed. Well, it's not simple, because force is not simple, but discussed at the beginning of the term. Yes?
What about
The standard deviation, well, it's because there's no standard deviation, it's a standard error, right? Because you deal with a population. It's not like measuring the heat conductivity of some metal which has a fixed value. You have a population. So this is barely statistically significant. So you could argue that the gain is really pretty close to zero, right? Why should it be? Well, you really want, given that we go way beyond force, you want all the students to understand force. Right? What good is it to learn about energy, collisions, rotations, this and that and the other, if you don't understand force? Right? So you really want to go not to 8, but you want to go to this diagonal line, right? Start at 80, gain 20. Start at 20, gain 80. As you can see, my data point is not very big, but very close to this line. This is perfect post-test score. The reason I'm plotting it this way is that I can compare to other universities. In the 90s, this professor at Indiana University collected thousands and thousands of data points from lots of different institutions. These are two-year colleges, which are on the low end of the educational spectrum, large state universities, and one lone Ivy League school. And notice that for everybody, the gain is low. In fact, interestingly enough, the two-year colleges have a bigger gain than Harvard students. But of course, they start out very, very low. They start below gorilla level. And they end barely at gorilla level. But there's a trend here. Notice that for each of those, they gain about a quarter of the maximum possible gain. All right? You go up here, and this is about a quarter of this. And here, 8 is about a quarter of 30. So traditional lecturing all across the educational spectrum does very little to address these misunderstandings. Now, when I saw that, for a moment I thought, well, Eric, maybe you're not such a good teacher after all. But that could obviously not be true, right? So I discarded that very quickly. So as I tried to explain this data point that you see here, I thought, well, maybe I have dumb students. But you know, that's a statement that's difficult to make at my university. So I thought about it some more, and then my twisted brain came up with the perfect excuse. What do you think it was? Put yourself in my position. You give this FCI, you see this very poor result. How do you, but you know you're a good teacher. How do you explain that to yourself? They're not motivated, but that would be the students. You know, students who come to Harvard are pretty motivated. Not enough time. Didn't work enough. I had a much better explanation than all of those. The test is bad. Very good. I mean, listen, Right? Heavy truck, light car, boom. Would you rather be seated in the heavy truck or in the light car? I thought maybe these are trick questions, right? Because, I mean, you don't need to take physics to know that the truck is going to be affected less than the light car. So I thought maybe they're just confusing words with concepts. Maybe it's just a misleading test. And I started, and unfortunately I don't have the time to go into the detail, but I did collect data. I started to do some testing of my own, where I compared students' performance on a standard textbook problem with a word-based problem on exactly the same concept. And what did I find out? That the students were perfectly able to do the textbook problem, but they struggled on the word-based problem. Why? Because they were solving problems by rote, by following a recipe without understanding the underlying reasons. More than half of my students fell in that category. They were simply attacking physics as a collection of facts and procedures. No wonder it's boring. No wonder it sucks. No wonder it is frustrating. Because you take away the baby with the bathwater. There's no beauty in doing that. The beauty comes from the understanding. Somebody mentioned understanding here earlier. But there was no real understanding. So what is clear is that it's not just the transfer of information or the teaching of procedures that matters. It's this making sense, this aha. Where did that happen? I've often asked myself, where did I actually learn the physics? Was it while I was sitting in the classroom listening to my professors and taking notes? Maybe a little bit, but most of it was outside of the class. When I went over the notes asking, you know, what does this mean? And I had the motivation because I wanted to become a physicist. Can we expect all the students taking physics to have that same motivation? No, an engineer might be interested in doing engineering, but still needs to understand physics. So for a while I thought, what am I going to do? And the first thing that came up to my mind was, maybe I better teach graduate courses. But it turns out that the solution presented itself serendipitously, by accident almost. What happened was the following. I told you that I was worried that my students would be offended by the simplicity of the FCI. They were not offended at all. They were horrified when they saw how poorly they'd done. So they asked me to organize a special session where we would go through every single question on the FCI. There was no time during the regular scheduled lecture, so I booked a room like this at night. At that time, we had about 200 students in the classroom. And I went through every question on the FCI. When I got to the heavy truck and the light car, I made a drawing of the truck on one side, the light car on the other. I drew the forces of gravity, the force of the road, the force of the truck on the car, and the car on the truck. And I turned around and I said, by Newton's third law, these two forces are equal in magnitude. What else is there to explain about it, right? And I could at once see that, you know, they were confused. So I said, does anybody have a question? They were so confused they couldn't articulate a question. You know how it is, right? If you're really confused about something, it's hard to articulate that confusion. I knew this was serious, so I thought I better try this again. So I erased the board, and I thought, you know, this time I'm going to bring in Newton's second law too, which connects force to acceleration. I'm going to show that even though the forces are the same, the effect on the heavy truck is much less than the effect on the light car. I gave the most brilliant explanation you can imagine. You know, there was a drawing of the truck there, drawing of the force there, all the forces, F equals ma. You know, I showed that the accelerations were different. It took me 8 minutes. Finally, I turned around, chuck dust everywhere. You know how it is, right? I was proud of my explanation. I looked. They were even more confused. And they could still not articulate a coherent question. I didn't know what to do. But I knew one thing. I knew that half of them had given the right answer. So, sort of on the spur of the moment, I don't remember exactly why I did, I said, why did you discuss it with each other? And something happened I had never seen in my life. The whole classroom erupted in chaos. They forgot about me. Totally. And what's more, in just about 2 minutes, they figured it out. I thought, how can that be? I take 10 minutes to explain, give them brilliantly clear explanations, and I get nowhere. And in 2 minutes talking to each other, they figure it out. But imagine that you have two students sitting next to each other. You know, John and Mary. Mary has the right answer because she understands it. John does not. On average, not always, but on average, Mary is more likely to convince John. But the important point is this. Mary is more likely to convince John than Professor Mazur in front of the class. Why? Because she has only recently learned it. And she still knows what the difficulties are that a beginning learner has. She still sort of knows what is going on in John's head. Whereas Professor Mazur learned it such a long time ago. To him it has become so clear that he can no longer understand why somebody does not understand it. It's what Steven Pinker calls the curse of knowledge. It's kind of ironic because I'm making a very strange argument here. I'm making an argument that the more of an expert you become, not the more qualified you are to teach, but the less qualified you are to teach. But you know, I'm sure that from your own experience, some of it must resonate and make sense. I'm sure that you've been in front of a classroom, a student comes to you and asks you a question, I don't understand this, that, and you look at this student and you think, you know, what is there to understand about this? Right? And then the student tries to articulate his or her understanding and you don't connect at all. Or maybe when you were a student, I certainly remember that from my time, I would often not bother asking the professor because I knew I'd get an answer that would go straight over my head. After class, I would go to a friend and say, hey, do you understand this? Can you explain this to me? So I thought, wow, that's amazing. If we can sort of use the common knowledge present in the classroom to teach each other, that would be great. And let's go back to education. If we think of education as a two-step process, right? One is the transfer of information, which is not enough. And two, what did I do with my remote? The assimilation of that information. In the standard approach to teaching, all of the emphasis is on the transfer of information. And the assimilation is left to the student on his or her own outside of class. Shouldn't be really, because I mean, let's ask ourselves, which is the easy step? I think we would all agree it's step one. Incidentally, for those of you who are familiar with Piaget, in his home country here, Piaget would have called that not assimilation, but accommodation, that second step, right? Where you try to accommodate the information that comes in with existing models. So what we should really do is we should focus on the hard step, not on the easy step, especially in the information age where the information comes at us from everywhere. So we should focus on that second step. We should ask students not to come to class to transfer information. No, we should ask them to have the information, to be exposed to information before coming to class. Read the book, or not the whole book, but a chapter before coming to class. Or if you're lucky enough to have a videotape of your lecture, watch a videotape before you come to class. And then in class, I focus on the assimilation or accommodation, however you want to call it, of that information. And I do that by teaching, by questioning. That's not something new at all. Socrates, 2,000 years ago, already said, we should teach by questioning, not by telling. Here we are in the 21st century, and we're still mostly teaching by telling. Some of you may actually point out that, ironically, I'm giving you a lecture about not lecturing. I'm actually very grateful to Jacques and Arjan to invite me because I miss lecturing, so this is a great opportunity to make up. No, but seriously, I'm here not to teach you something conceptually very difficult. So I'm not here to teach you, I'm here to motivate you to perhaps look at how I change my approach to teaching and reconsider your own. So there's a distinction between teaching your discipline and what I'm doing here in front of you. So I come into the classroom. I require my students to either read a chapter or watch a lecture before coming to class. And then I talk a few minutes and I pose them a question. After I pose them a question, I give them time to think. It's silent. How often can you actually think? I've been firing information at you now for an hour. If you're tired, I don't blame you, right? Because your mind has not been able to wander. Because if your mind wanders, you lose track of what I'm saying. We're very bad at multitasking. We cannot think and listen. We either think or we listen. Right? But here, I'm silent. I actually give students time to think. Then I poll them. If neither too many nor too few have it correct, I tell them, turn to your neighbor and try to convince your neighbor of your answer. Now, it's important that it's neither too many nor too few, right? If 80% gets it right on that first poll, they turn to each other, they agree, they start talking about something else. Or, on the opposite extreme, if, let's say, fewer than 30% have it correct, right, they turn to their neighbor and they may actually talk the neighbor into the wrong answer because most students have the wrong answer. So it's important to tailor the level of the questions to the audience. That's not obvious in the beginning. Okay? That's not obvious at all. Then I poll them again, and I wrap up with an explanation, which can either come from me, or I can say, you, John, why don't you explain the answer you gave? I mean, I can make it a class discussion. The learning, and then that cycle repeats until the course is over, the class is over. And of course, the learning takes place in this period of discussion. Let me show you a compressed video, compressed in the sense that I've taken 5 minutes, but I'm only showing you 1 minute, of one such cycle. So I start by reading the question with the students.
So we have a rectangular loop that is placed in a uniform magnetic field in the direction indicated by these arrows. So the question is, what are the magnetic forces on the 4 different sides of this loop? So take a minute to think about this and then enter your answers.
They're thinking. It's silent. I do not want them to talk to each other. I can see on my
Please enter
screen
your
the
answers.
distribution.
We have a
I don't show the distribution.
disagreement clearly here. So turn to your neighbor and see if you can convince one another of the correct choice.
Right, it goes out of the page and the top goes in, so they cancel each other out.
There is a torque.
There is a torque.
How do you know that?
I said torque.
What did you say? But how can it be a torque?
Initially, we had sort of an even split. And now we have an absolutely overwhelming majority for choice number 2. The bottom of this loop is pulled towards you.
I do show them the second distribution. They don't see the first distribution, but they do see the second one, right? And you saw maybe that initially there was an even split between answers 1 and 2, and after that, an overwhelming majority for answer number 2, which is not unusual. So what's going on here? One is, it's active, not passive. It is impossible to sleep through my classes because every few minutes your neighbor will start talking to you. Believe it or not, some students actually complain. But also, now there's a two-way flow of information. I don't have to wait till the exam or homework or whatever to find out that my students don't understand something. I can see it then and there and do something about it. There's a continuous stream of information coming back from the students at me. Moreover, there's a continuous opportunity for the students to assess their own knowledge. Imagine that after the second vote, you're in the few percent who still has the wrong answer. You see that most of your classmates get it right, but you're there. No panic, because it's not going to affect your grade, but it tells you in time, you better look at this before the exam or you'll be in trouble. So there's continuous formative assessment of students' understanding. You want to try it? Yeah? Did you all read that handout on thermal expansion? I asked Arjan, you did not distribute it? Just kidding. But you know what that means. I was thinking of doing a question on thermal expansion, and since you didn't read, that means I'll have to lecture you on thermal expansion. Okay, so let me give you a little lecture on thermal expansion. Solids, all of them, to a different degree, expand in volume when they get hotter. And this phenomenon is particularly pronounced for metals. So for example, when people lay train tracks, the different sections of the rail, the different segments, you leave a little gap in between. This is why when you're in a train, you hear this clickety-clack sound of the wheels. When the train doesn't go too fast, you hear this clickety-clack sounds as it goes over these gaps. And you may wonder, why don't they put them together? Well, if they put them together and the rail heats up, it can't expand in the direction of the rail. And as this picture from a railroad in India shows, the rail will buckle with pretty disastrous effects. It's also important in the engineering of buildings, buildings that have steel beams. You need to take into account that expansion of the metals. Now, metals expand, and in fact, almost solids expand, but it's particularly pronounced in metals because they're made from atoms, and atoms get further away from one another when they heat up. So this is a cold metal, that's a hot metal. Cold, hot. That's all there is to it. You may wonder, why do they get further away from one another? They get further away from one another because what we call temperature has to do with the thermal motion of atoms. Atoms don't sit still. So if you were atoms, you wouldn't sit there like this. You'd actually be shaking. And the amplitude of your motion is what we call temperature. So these are cold atoms. These are hot atoms. Well, if you have a bigger amplitude of the motion, you need to take more space, right? And therefore, you push all the other atoms apart, right? Questions? Now look, you better ask questions, because if you don't ask questions, I'm going to ask my question. And I don't know, I'm not an engineer. You have to have some mechanism that can absorb the expansion. Yeah. Ice is an interesting material because as it melts, it actually densifies, which is why ice cubes float and icebergs float. But that's a phase transition. I'm talking here about staying completely within the realm of solids. Even ice will expand if it's very cold ice and it heats up. Right? But at the phase transition, something strange happened. Good, I'm glad there are questions, because here's something, look, I mean, one thing I could do is I could black out the screen and I could simply ask you a question. When metals heat up, they expand because A, the atoms get further away from each other, B, the atoms stay in the same position, D, the atoms get closer together. But that would not be interesting, right? Because then I'm just giving you information and you're giving the same information back to me. I'm going to see if you can take this concept of atoms getting further away from one another and transfer it to a new context. Yes? That's a good question, but basically imagine that they need more room because they're taking more physical space. Now, at the atomic level, things are a little bit more complicated than that, but to answer the question I'm going to ask, the mental model of simply, needing more space because you have more motion works perfectly well. Yes?
What happens with plastic? What happens with plastic that contracts when we heat it up?
That's a very good question. So plastics are very particular materials made from polymers. We're going to stay away completely from polymers. And if I get into all of your excellent questions, this talk is going to turn into a lecture on solid state and soft matter physics. I want you to focus on that picture, right? I mean, the atoms getting further away from one another when they're hotter? Hot, cold, hot, cold. Yes? So in other words, let's take, I think I understand your question. You're going to tell me whether that's right. Let's imagine that we put a box around those atoms, right? We're pushed in there, and now we heat it up. Do they still move out? Look at the rail here, right? The rail, in a sense, is that pressure. The force is so big, you can't. Okay, so it'll buckle into in some other direction. Oh, good, I love it. You know, usually most audiences where I give this question, we don't ask anything. Yes, last question, because you're all way beyond the question I'm going to ask you.
I'm wondering if the atoms follow a specific direction. I mean, it can go always like this.
That's a good question. I mean, let's look at this picture, right? All the atoms go in different directions. This one moves up. That one moves up and to the left. That one moves to the left. That one moves to the right. This one doesn't move at all. Why doesn't that one move at all and the others move? Well, simply because I have made those two images and I put them on top of one another, and I centered the pictures on the central atom. But that's completely arbitrary. I could have put this one on top of that. Then what would have happened to this one? It would have moved at an angle. And this one would have moved down and to the right. And this one would have moved twice as far down and to the right. So the key point is not in which direction they move. The key point is really, I'm really happy you asked the question because I made a slide for it. All of the atoms, not just the 9 that I've shown there, all of them get further away from each other. I think you're ready for a question here. So let's go there. And remember, these are the instructions. I'm going to ask you the question. You're going to think about it. You're not just going to jump to an answer. You're going to think about it and then choose an answer without talking to your neighbor. If you talk to your neighbor, I'm going to run up at you, and I'm going to ask you to talk to the entire audience here. So you better be silent. After you have voted, I'm going to ask you to turn to your neighbor. And chances are that you're sitting next to somebody you know. And chances are that that person maybe has exactly the same answers you have. Stop talking to that person. Your task is to find somebody who has a different answer, right? So if you turn right and that person has the same answer, you say, thank you very much, and you turn left. And if that person also has the same answer, you tap the person in front of you on the back and you say what answer. If necessary, walk up, but find somebody with a different answer. You know, walk around, but find somebody with a different answer. Once you've convinced that person, or that person has convinced you, you must find somebody else. The process does not stop until I stop you, okay? All right, so here's the question. Consider a rectangular metal plate with a circular hole in it. When the plate is uniformly heated, the diameter of the hole, 1, increases. 2, decreases. No, stays the same. Pardon me, I can't read. 3, decreases. I'm going to give you 1 minute to think. And think about explaining it in terms of the atoms getting further away from one another. And if you've already answered, ask yourself, how am I going to convince that person next to me that I am right and he or she's wrong? No talking yet. Another half minute. $20 seconds left. 15, 10. So at this point, if you don't know, make it a game. But do press a button, 1, 2, or 3, okay? Okay, so now find somebody who has a different answer. Try to convince that person. Go ahead, the floor is yours. 30, 15, 55. 13, 50, 55. 13, 15, 55. Je suis prêt dans 5 minutes.
Pas de souci. Oui, on a un peu de temps.
Oui.
Il semble qu'il y a eu un petit problème de channel sur certaines appels, mais c'est pour ça. On ne va pas changer maintenant. Certainement, on va changer.
Bon.
Quand même,
Absolument, absolument. Autant que vous voulez. Moi, je m'amuse. On voit tous les gens. On les voit tous. Parfait.
Cet après-midi pour la conférence des recteurs et je ne peux pas rester pour le...
mais je suis souvent ici en Suisse, donc...
J'aurais vraiment aimé continuer la discussion, mais on peut se revoir.
Et si vous n'êtes jamais à Harvard, vous me faites savoir.
The thing is wrong.
What?
Si vous voyez sur une chaise, il y a un gars tout au fond, contre le mur, qui a laissé sa sapette sur la chaise. Il faut demander. Moi, je pense qu'on retrouve
Look at that. I mean, look at how you all got engaged. You got all fired up. See there, they're still, look at them there, they're still, hello, hello. Everybody gets fired up. You should have seen it from here. And he's still talking, I can stop, right? I'm sure that by now, you have forgotten that I am not here to talk about thermal expansion. I'm here to talk about physics. The answer to this question doesn't matter. Look, you should see their faces. Imagine I'd just given my little lecture on thermal expansion, and then I would have said, and now we're going to apply this to a rectangular plate with a circular hole in it. If you take this plate, and you uniformly heat it, then the diameter of the hole will, I'm going to keep you in suspense a little bit longer here. You would have written it down, but you would not have been engaged this way. Now, I'm sure that if I were to say, goodbye, I've made my point, you were engaged, you know, you would, and I'd leave, you would come running after me saying, what's the answer? Right? You've taken ownership of that learning. So why don't you enter what, I know I cut the discussion short, which is bad, but we need to move on. Why don't you re-answer that question, entering the answer you believe to be true now. And I know I have not given you enough time here, which is bad. But we need to move on. And you know, before I tell you the answer, I think I'm going to keep you in suspense a little bit longer and sort of analyze what happened here. Because what did you do, right? I made you make a commitment. You pressed a button, committing yourself to an answer to various degrees. Some of you may have made the commitment guessing. Others may have made the commitment with more conviction. Then you had to externalize your answer. You had to turn to your neighbor and say, I chose because blah, blah, blah. And during that discussion, the answer moved from a fact, from, you know, it expands or it contracts or in between, to the reasoning of the answer. So much assessment is just about the answer, but here you started to actually talk about the reasoning. But, and this is really the most beautiful point, and you've done a fantastic job showing that, you became emotionally invested in the learning process. You're not going to let me leave now. Even though, let's face it, you know, is this so exciting, holes in plates? Now, I thought I gave a pretty brilliantly clear explanation of thermal expansion, but I have some bad news here. Only 30% of you got the answer right. So you've already helped me make another very important point. Lecturing is not very good at explaining things. Otherwise, 100% of you would have gotten it right. Only 30% got it right. Now, the method doesn't work that well when only 30% gets it right. It's what I consider the absolute lower limit of a question. So let's see what happened after the discussion. And wow, a miracle happened. Because it actually went up, and it went up to become the most popular choice. Initially, the distribution was, because the right answer is, drum roll, answer number 1. And look at the distribution before and after. Here, the red one is before, the blue one is after. What's that 9 and 10 there? 1%. There's some people who have trouble finding the right button. So even though only 30% of you got it right, simply by the sheer force of logic reasoning, after discussion, 42% got it right. Can many of you see right now? I don't want to be responsible for you lying in bed tonight thinking, why does this hole get bigger? You know, you've known it all along. Imagine you have a jar of marmalade in the refrigerator, or cornichon, or anything else, right? Glass jar, metal lid. The metal lid is a ring with a plate. You take it out of the refrigerator, you can't open it. What do? You run the metal lid under hot water. The ring expands. You say, that's unfair. This is a rectangular plate. That's a ring. It's not the same thing. Okay, well, then imagine this. Imagine we have a rectangular plate without a hole in it. No hole. We take a pen and we draw a circle on it. Now we heat up the plate, and the plate expands. What happens to the diameter of that drawn hole? That drawn circle, pardon me? Everything gets bigger, so that has to get bigger too. You say, well, that's unfair because there's no hole. If there was a hole, then the atoms at the edge would expand into the hole. But let's think about that for a moment. You're really engaged. I love that. So let's consider the atoms at the edge of the hole, right? It's a beautiful day out here. We could all go outside, form a big circle. We are the atoms at the edge of the hole, right? So there we are. We're holding hands, huge circle. We are the atoms at the edge of the hole. Now imagine we're stepping in towards the center of the hole. What happens to the diameter, to the distance between us? Gets smaller. It can't get smaller because, you know, the other person is shaking more, right? The only way to make the distance between us larger is to take a few people away, but atoms don't disappear like that, or to make the hole larger. You won't forget this. And again, you are probably thinking that I'm here to teach, talking about physics. You've forgotten that we're really to talk about PI, peer instruction. So let me wrap up, 5 minutes, okay? Is it any good? How could you answer that question, is it any good? Well, the first thing to do is perhaps to see how students do on the FCI in my class after I switched. As a physicist, I've been to many, many conferences. And you know, you hear people present their data and they say at some point, I'm going to show you some typical data. I've learned that that's a code word. It means these are the best data I've ever obtained in my entire career. Well, I'm going to show you some very atypical data. I'm going to show you the data I obtained the first year I taught with peer instruction. Here's the pretest. This pretest is incredibly stable. They're among the most reproducible data I've ever obtained in my career. And here is the post-test, very significantly better. Notice that we've eliminated all the gorillas. Yes, we still have some students who do not understand Newtonian physics, but the fraction is very much smaller. I was so excited when I saw those data. I submitted an abstract to the American Association of Physics Teachers summer meeting in Vancouver. I'd never gone to that meeting. And nobody knew about me, so all I got was an 8-minute contributed talk. So I flew out to Vancouver, and I thought, you know, I have to be sure when I show those data to convince the people that I did not teach to the test. I had never in the classroom or on homework used any questions that resembled the FCI questions. I didn't want to, you know, contaminate my results. So I spent a precious 4 of my 8 minutes documenting that I'd not taught to the test. At the end of my presentation, someone in the back raised his hand and says, don't worry about teaching to the test. We've tried it, it doesn't work. So now we have a very substantial improvement, and instead of an 8% gain, we have a 16% gain. And in subsequent years, I've been able to raise that to tripling the gain, 24%, simply by a better choice of questions in the class. This question about the hole in the plate, for example, if this were a real class about thermal expansion, would have probably been, that would be marginal, right? And other institutions, these here, that have introduced interactive learning, almost all of the data, with one single exception, have gone up. And if you take just the average of all data, you see that there's a doubling of the learning gain. But this is just force. What about problem solving? I knew my colleagues would ask me that question. So I decided to do something I had never ever done, namely to repeat an exam. I'd kept meticulous data. So I was able to go back to an exam I'd given in the second year that I was teaching and reconstruct this histogram. And you know, we keep only 3 years of exam on file in the library, but even if a student had seen all of my exam, he or she would have immediately concluded, Professor Mazur never repeats a problem. So I said to myself, as long as the average is about the same, I'm happy. I was actually expecting it might even go down a little bit because in 1991, I decided not to do any problem solving in class. I would often interrupt the class, say, let's now apply this to a problem, and I would solve the problem on the board for the students. But in 1991, I decided that was not a very useful thing. Imagine you're learning to play the piano. You don't go by going to a concert hall and listening to Murray Pariah. Or imagine you're training for a marathon. You don't do that by sitting in front of the TV, eating popcorn, watching DVDs of marathon runners. You have to do the running. You don't learn physics problem solving by watching a Harvard professor solve problems. You have to do it. So yes, the students still had problem solving, but it was not doing it by example. So I thought, you know, maybe their problem solving performance will have suffered somewhat. But you know what? It actually got better. Statistically significantly better. It went from 62% to 68%. Several times the standard error. The p-value, for those of you who know about statistics, was 0.01. 0.01, yes, exactly. And we've certainly helped the students at the bottom. So what does this mean? This means that better understanding leads to better problem solving. That's kind of obvious, right? If you think about it, I'm making sort of an obvious statement here. But, and this is probably the most important message I want to get to you today, good problem solving does not necessarily mean understanding. My students before were perfectly able to solve problems, but they did it by rote. And I was fooling myself into believing that I was a good teacher. But as I said, it was really not the case. So let's reflect for a moment more as what happens in a lecture like mine now, here today. It's very hard to pay utmost attention. The mind likes to wander, but there's no time to wander because there's this continuous stream of information. And the fact that the brain reacts to that adversely was recently highlighted by an article that I saw out of the Media Lab at MIT. At the Media Lab at MIT, they developed a little sensor that you can wear around your wrist that measures electrodermal activity. The great thing is it's portable, so you don't need electrodes in the brain. And most of the article is devoted to showing that the neurological activity measured here correlates one-on-one with the brain activity. But one of the things they did was to give that sensor to a student at MIT who wore the sensor for a full week. And there's a graph in that paper, the DOI is here at the bottom, that shows for the student for 7 days, day 1, day 2, day 3, day 4, the neurological activity. And here, I don't know why time at MIT starts at 4 o'clock in the afternoon, but I have no idea. This is time. And then this is too small for you to read, but it shows, it labels the activities. I want to draw your attention to the activities labeled class. The trace goes flat. I want you to compare that. I want you to compare that to the activity labeled sleep. The brain is very active during sleep because short-term memory gets written to long-term memory. In other words, here's where we get back to sleep. Students are more asleep in lecture than they are when they're in their beds. Now, there's only one activity. Don't look at the screen, right? Just look at me here. There's one activity that matches class. Think about it. What would that be? There's one activity. Watching TV. Look here. There it is. Watching TV. And this is somebody that people in neurobiology knew for a long time, and in brain sciences. You know, when you sit in front of the TV, your brain shuts down. There's all these alpha. There's so much information coming at you. There's no time to think, to wonder, to do anything useful. I'm sure you've gone to a movie of a book that was made of a book that you read. And very often, I think this is almost universally true, people enjoy the act of reading more than watching, in part because it doesn't correspond to their imagination, but mostly because the imagination is gone. When you watch the movie, there's this continuous stream of information. When you read a book, you can pause and think and dream and let the mind do what it likes to do, right? But in the movie, you can't. Now, why would a class be different from TV? Right? There's no reason. So you don't pay utmost attention. You walk away thinking you know it. You all thought you knew it about the expansion of the atoms. You know, and I have that often with colloquia. We invite somebody from Yale or Stanford or whatever to give a colloquium. They give a colloquium. It's a fantastic performance. Right? 2 hours later, I'm in the hallway of my building. A colleague comes by and says, "Did you go to that colloquium this afternoon?" I said, "Yeah, I went." "How was it?" "Ah, it was a fantastic colloquium." "Really? What did he talk about?" And that's when you realize that, yeah, it all sounded very good, but you can't reproduce it. Right? So you have this feeling that you know it, mostly because you've not been able to think about it and you've not been confronted with any misconceptions. But it really is a false sense of security. It's an illusion. So education is not just about transferring information or getting students to do what we do. We want the next generation to solve the problems we have not been able to solve. Society faces a lot of problems. And therefore, I think active participation is an absolute must. Lastly, let me remind you of what I began with. It's not the technology. We could have done this without any technology, by just having a show fingers on the chest, right? You could all have done this, and I would have had a pretty good sense of where you were. So if you're interested, there's a, I know it's short time right now, but in December in Beijing, there's a conference on peer instruction. This is a resource, a social network for peer instruction users where you can find other instructors, peerinstruction.net. And if you want to download my slides, you can go to this URL right here. You don't need to write it down. Just go to Google, enter my last name, and then hit this I'm feeling lucky button, and you'll have a copy of my slides. Thank you very much. I'm sorry I went over.
Merci Eric pour cette très stimulante présentation qui illustre parfaitement qu'on peut être un très grand chercheur, aussi un excellent enseignant, merci Nathalie, et très impliqué dans l'évolution de l'enseignement. On va prendre quand même le temps, si vous pouvez encore modérer votre soif, quelques minutes, pour prendre juste quelques questions. On n'a pas le temps d'en prendre trop, mais quelques-unes. On va peut-être vous donner un micro. Et il faudrait parler assez près du micro, s'il vous plaît.
I'll ask the question in English. So my question is, how much time do your students spend at home studying and doing homework as compared to the time they spend in class? And I explain why I ask the question. I teach physics myself here, and my experience is that here students spend from 8 a.m. to 6 p.m. in class. And simply after that, they won't work at home. So I tried very lightly to apply your method, but I was much frustrated by this fact.
That's a good point. That's a good point. I mean, if they go, so in the United States, or at least at Harvard, a student typically takes 4 classes, and each class is on average probably 3 hours. So 4 times 3, that's 12 hours. And then there are, of course, discussion sections, laboratories, and so on. But there's no way it is a 40 hours a week, right? I mean, if you keep them completely busy in a lecture environment, there's no time to do any reading. That's a serious problem. In fact, we get to a question that I was asked in the break. You know, do your students actually do the reading? And I would actually like to get your feedback on there. I mean, why don't students come to class prepared? I mean, I've written down the things that I typically hear when I ask instructors. 1, they don't have time. 2, they're not motivated to learn. 3, their instructors take away the incentive. 3, they do not have the requisite skills. 5, some other reason. Or, you know, maybe you're among the lucky ones where they actually do come to class prepared. I would like you to use your clicker one last time. Oh, and by the way, I'm sure that Nathalie wants them back. They don't control your microwave or your television or anything, so as you walk out, please return them back. So why don't you indicate what you would choose as the response? I'm very curious to hear that. You know, one thing I tell my students also is, look, at some point you have to read the material, right? You can read it before class to prepare yourself for class. You can read it after class to understand what happened in class. Or you can wait till 2 weeks before the exam to quickly try to learn everything. There's a conservation principle here. It's going to take the same amount of time no matter when you do it. When are you going to derive the most benefit from it? I think everybody agrees on that. It's going to be before class. Let's see the distribution here. Did I click? There. So we have 3 popular answers. 1, they don't have time. 2, they're not motivated to learn. 3, their instructors take away the incentive. So let's start about the motivation, right? Did we read when we were students? I didn't, I'm sorry. I didn't, and I know most of the other students did not read before coming to class. Was I motivated to learn? I think I was. Did I not have time? I certainly partied a lot when I was a student, so I'm not sure that that is a valid excuse too. I think, personally, I would have chosen number 3. We, instructors, you and I, take away the incentive. We didn't read before coming to class because we did not have to. The instructor was reading for us. In fact, I discovered that the hard way. First year I did peer instruction. I would start the class by asking a couple of quick survey questions to see if the students had read it, had read what I'd asked them to read. And to my horror, I would discover that 50% had not read. Oh my God, what do you do then? Right? Because how can you start asking questions if they've not read? So what I would do is would say, okay, let's take 20 minutes to quickly summarize what you should have read, only to discover that that's exactly the wrong thing to do. Because you're telling the students who do not read, don't worry, if you don't read, Professor Mazur will tell you what you should have read. And you're telling the students who have read, you fools, you've wasted your time. So I think the first thing that we have to do is really change our own behavior and demand reading. Now, if there's really a lecture schedule that keeps the students busy from 9 to 6, that's perhaps also another constraint that needs to be revisited and thought about. So that would be a serious concern of mine. Now, if you're interested in finding a good way to get students to read before coming to class, there's a technique called just-in-time teaching, JITT. And if you go to www.jitt.org, you can read more about this technique, which is a very good complement to peer instruction. Another question? Yes.
I have a question, actually. What happened to your notes? What do you distribute to your students?
So I still give the notes before class, but I don't lecture from them anymore. They have to read the notes before coming to class. That's actually part of the reading, yes.
Hello, my work is in, like that, okay. My work is in the effect of technology on students. Have you noticed in the last 5 years or so a change in student behavior because of technology?
Well, I mean, there are many laptops, and there are many laptops that are open, as we see. There are few in this room, which makes me very happy. There are some instructors who say we should forbid students from bringing laptops to the classroom, which to me is a totally ridiculous thing because, yeah, they might close their laptops, but you don't control their minds, right? They might sit there and still be daydreaming. I think if I look at my colleagues while we're at colloquia, you can sort of measure the quality of the colloquium by the number of laptops that are open. The more laptops open, the worse the colloquium. And you know, I know that when I go to a meeting that's boring, I mean, I'm really happy that I have my smartphone and I can check my email and do other useful things. I think the students are like that too. If the perceived value of what they're getting in the classroom is not high enough, their minds are going to be wandering. The urge to do other things like Facebook or email or you name it, it's going to be high. Is that their problem? No, it's really our problem. It's because we're not offering them an activity that is of a high enough value. When you teach with peer instruction, during the times that they talk, all the laptops are closed. They're not looking at Facebook. They're not looking at anything. Now, is it all beautiful and good? Well, you see, not everybody improves. Are they giving me high marks on my evaluations? The evaluation has not changed very much because it measures personality more than anything else. One thing has changed, the nature of the complaints. There's not a single student who writes, Professor Mazur is lecturing straight from his lecture notes. I've taken care of that very effectively. But you know what they write now? Now they write, Professor Mazur is not teaching us anything. We have to learn it all ourselves.
So how do you think that positive discrimination affects education?
Positive?
Positive discrimination. When you're accepting students, you know that there are sometimes like this positive discrimination according to the race or according to, well, race, according to the background, for example. And in India, they have, what is it called? I forgot. In India, for example, they have reservation for lower castes, which means that they can get into university with lower grades. So I'm asking you, how do you think that affects education? Do you think is that a good idea?
I'm very happy you raised that issue, because you touch on a very profound issue, namely the issue of assessment, which I didn't touch at all on. The assessment, which is the basis for giving grades, right, is sometimes called the hidden curriculum, because especially in many Western societies, I think there are a lot of students whose habits are completely determined by the assessment. Students study not in order to learn. No, they study in order to pass the assessment. And let's look at the nature of the assessment. I mean, you can go on the web and type in examination and do a Google search on images of examination, and you can already imagine the image you will see. Rows of desks, people like this, separated from one another, no books, no computers, no nothing, no cell phones. Do these images give you pleasant memories? If you are, I think you're in trouble, because you're not in the company of many other people. I think most of us found it and still find it a very frustrating experience. It's one of complete isolation, isolation from other people, isolation from information. Have you ever, since leaving college, encountered a situation similar to that represented by one of these images? No, because life is collaborative. So I think that the way we assess is not very meaningful. Right? We are not measuring the type of skills we know. And that's why I'm really happy to hear about what you said about India, because I know plenty of examples of graduate students who come to Harvard who have grades that are much lower than that of others, but who are really, really good at becoming a scientist. And I know other students who get in with, absolutely stellar grades from stellar institutions, but they can't do any useful research because they don't have the right approach to thinking and learning. So clearly, the way we assess, the way we discriminate, I think is not very successful. And we know that, right? I mean, there are a lot of brilliant people who have not even finished high school, and there are a lot of people who have brilliant grades and end up failing in real life. So I think, but unfortunately, I don't think we have time to really get into depths here. We really need to rethink the nature of the assessment. I'm going to make a very bold statement right now. I think that assessment is the silent killer of educational innovation. No matter how innovative you are in the classroom, if we do not change the way we are assessing our students, we're never going to be able to really have an impact in education. But it's a long subject. I'll just go way beyond this, and the coffee will get cold.
Mais merci beaucoup. Vous voyez qu'il y a encore plein de sujets à explorer. Cette collaboration entre la HES, Université et SFDN est inédite, mais elle se reproduira sûrement. Et peut-être on pourra parler de l'assessment la prochaine fois. On voulait juste laisser un petit souvenir à Eric de cette journée, quelque chose typiquement suisse, mais qui n'est pas une montre. J'ai demandé à Ariane de le remettre parce que je pensais que ce serait plus agréable de l'embrasser elle que moi.
Ah, merci. Merci beaucoup, merci. Magnifique.
UNIL HSSO. UNIL HSSO. It's a great. I will show you.
Oh, okay.
Okay. Merci à vous toutes et à vous tous d'être venus. L'apéritif vous attend dehors et surtout un immense merci à Eric Mazur pour sa présentation. Merci. Excellent. Non, on peut parler anglais.
Oui.